Let's proceed to AC power analysis. Power is the most important quantity in electric utilities, electronic and communication systems, because such systems involve transmission of power from one point to another. Also, every industrial and household electrical device such as fans, motors, lamps, TVs, PCs, etc. have power ratings that indicates how much power the equipment requires. So we have instantaneous and average power. So instantaneous power measured in watts is the power at any instant of time. So assuming the passive sign convention, our instantaneous power given by P of t is equivalent to V of t times I of t. For example, if we have this passive linear network with a sinusoidal source where Vt is given by Vm cosine omega t plus theta of V, then we have the current Im cosine of omega t plus theta of I. So our instantaneous power is substituting V of t and I of t, we have this equation. Now using this identity, we will arrive with this equation. So as you can see, the instantaneous power has two parts. So the first term is time independent, and it only depends on the cosine of the difference between the phase angle of the voltage and the phase angle of the current. Now the second term is a sinusoidal term with a frequency of 2 omega, which is twice that of the voltage or the current. Now graphing the instantaneous power, we have this sinusoidal function where our peak is just 1/2 Vm times Im. Now the average power measured in watts, the average of the instantaneous power over one period. So since instantaneous power changes with time, it is difficult to measure. So average power is used. So in fact, power meters measure average power. So to get the average power denoted by capital P, it is the average of the instantaneous power over one period. We integrate the instantaneous power from 0 to t and over one period. So substituting this equation to this integral, so we have this line. Now since the first term is a constant, since the first term is a constant value which does not depend on time, so we can factor out this one. So we have this term and this term. Now looking at the second term, if we integrate a sine or a cosine function from 0 to t or over one period, the answer is 0. Why? Because integral is just like getting the area over one period. So we have this positive cycle, the negative cycle. So integrating that over one period, so this cancels out. So we have positive and negative. So our average power, we are left with this. P is just equal to 1/2 Vm Im cosine of theta V minus cosine of theta I, which is looking at the graph, this dashed line, blush blue line. This is our average power. So now we'll take a look at the average power absorbed by an ideal resistor and the average power absorbed by a purely reactive element. For an ideal resistor, ideal resistor, our voltage, example, this is our voltage. The current is in phase with the voltage, meaning the difference between the phase angle of the voltage and the current is 0. This is 0. The cosine of 0 is just 1. So for a purely resistive element, we have our average power is given by 1 half Vm Im, or can write this as Im squared R, or 1 half Vm squared over R. Now for purely reactive elements, if this is our V, the difference between the phase angle of the voltage and the current is positive 90 or negative 90. So depending if it is a purely inductive uh, element or a purely capacitive element. For a purely positive element, we have, this is our I, or positive 90. For purely inductive element, we have this I, or negative 90. Now cosine of positive or negative 90 just equivalent to 0. So the average power absorbed by a purely reactive element is 0. Now for example, find the average power absorbed by each of the 3 passive elements. So we all know that a purely reactive element does not absorb average power. So we have our average power for an inductor is just 0. The average power for our capacitor is 0. And using nodal analysis to solve for the power of the resistor, denote this as V, our reference. So KCL at V, we have V minus 20 over J2, which is this branch, plus V over 2, which is this branch, plus V minus 10 over negative J2 equal to 0, which is this branch. Now solving for V, we have 1 half plus 1 over J2, 1 over J2 equal to negative J5, or our V just equivalent to negative J10, or we have 10 angle negative 90 volts. Now this is our magnitude of Vm. Getting the absorbed power by the resistor, we have 1 half Vm, which is 10 squared over R. Now 25 watts. Now checking this answer, we can solve for I1 and I2. Now solving for I1, we have 20 angle 0 minus V over J2. We have 5 square root of 5 angle of negative 53.435. Now for I2 is equivalent to V minus 10 over negative J2 equal to 5 square root of 2 angle of negative 45. Now getting the power by the 20 volt source, we have, using the passive sign convention, we have negative 1 half times 20 times 5 square root of 5 cosine of the angle of 20 volts is 0 minus negative 63.45. So plus 63.435. We have negative 50 watts. So our 20 volt source is supplying 50 watts. So for our 10 volt source, we have, following the passive sign convention, 1 half times 10 times 5 square root of 2 times cosine of the angle of our 10 volt source is 0 minus negative 45. So we have plus 45 equal to 25 watts. So our power supplied is equal to the power absorbed. Now for maximum power transfer. So an independent voltage source in series with an impedance ZTH or an independent current source in parallel with an impedance ZTH delivers a maximum average power to the load impedance ZL, which is the conjugate of ZTH, or we have ZL is equal to conjugate of ZTH. Now, if we have this network, it delivers maximum power to ZL if our ZL is equivalent to the conjugate of ZTH. So meaning if we have GTH is equal to RTH plus JXTH, and we have ZL equals to RL plus JXL, so our ZL should be equivalent to RTH minus JXTH. How did we arrive at this? Now getting the current, we have VTH over ZTH plus ZL is equivalent to this equation. Substituting ZTH and ZL. Now getting the power, which is 1 half magnitude of I times RL, we have this equation. And then getting the partial derivative with respect to XL and our partial derivative with respect to RL, and then equating them to 0, then solve the values for XL and RL, we will arrive with this. Substituting the values for RL and XL, we have our P max is just equivalent to VTH squared over 8 times RTH. So for example, find the value of ZL to obtain maximum power transfer. So first, let's solve for Thevenin equivalent circuit as seen in terminals A and B. So for VTH, so solving for the open circuit voltage is our VTH. So by VDT, our VTH just equal to 8 minus J6 over 8 minus J6 plus 4 times 10. So we have VTH equal to 10 times square root of 5 over 3 with angle of negative 10.305 degrees volts. Now solving for ZTH, since we only have an independent source, we can turn it off and find the Z equivalent as seen by terminals A and B. Yeah, this is our ZTH. So ZTH is equivalent to, we have 4 parallel with 8 minus J6 and in series with J5. We have our ZTH is equivalent to 44 over 15 plus J67 over 15 ohms. Now for maximum power transfer, or ZL, would be equivalent to the conjugate of ZTH. So we have 44 over 15 minus J67 over 15. Now solving for the maximum power transfer, equivalent to the magnitude of VTH is 10 square root of 5 over 3 squared over 8 times our RTH. So 44 over 15. This is equivalent to 2.367 watts.